Modern cargo trains are the most efficient way to move freight across America. Think again. Over 150 years ago, without GPS, without computers, without diesel engines, American engineers connected to continents using Victorian-era brute force and brilliant engineering that took just 6 years to complete. While we obsess over building new highways and airports, we've overlooked the fact that a railroad built in 1869 still carries freight today. Today, you're going to discover 5 incredible engineering achievements from the Transcontinental Railroad that changed civilization forever. Get ready to understand why railroad engineers of the 1860s solved problems we're still wrestling with. In May of 1869, something impossible happened at a place called Promontory Summit, Utah. 2 railroad companies, one building from the east, one building from the west, finally met after 6 years of brutal labor in deserts, over mountain passes, and through wilderness that seemed unconquerable. When they drove that golden spike into the ground connecting those final rails, America was officially united by iron and steel. But here's what most people don't realize. That same railroad route is still active today. The engineering principles used to build those 2,000 miles of track in 1869 are the foundation of modern American freight railroads. In the next few minutes, we're going to explore how Victorian engineers accomplished in 6 years what many thought would take decades. This story reveals why the Transcontinental Railroad wasn't just transportation, it was the greatest engineering achievement of the 19th century. The Transcontinental Railroad, the engineering marvel that built a nation long before modern surveying equipment existed. Railroad engineers had to physically walk through mountain ranges to find the best routes. Theodore Judah, the engineer who surveyed the Central Pacific route through the Sierra Nevada, spent days on foot identifying Donner Pass, a single ridge crossing that would have taken weeks of blasting if engineers had chosen the wrong location. What made this achievement special was that Judah understood something crucial. A single ridge meant fewer tunnels, less dynamite, and a route that physics would allow as steam. Locomotive to climb. Modern engineering records confirm that the Central Pacific's route through the Sierra Nevada required 15 major tunnels, with the longest tunnel 6 taking 14 months to blast through solid granite, while workers faced brutal winter conditions at 7,000 feet elevation. Yet despite these obstacles, the route remained the best possible engineering solution. For today's railroad historians and engineers, understanding Judah's route finding reveals why Victorian engineers succeeded where modern surveyors might fail. They combined intuition with mathematics. But the engineering challenges were just beginning. The Dale Creek Bridge, when engineers built where nothing should stand, spanning 650 feet above a creek in Wyoming. At a height of 125 feet, the Dale Creek Bridge presented an engineering problem that seemed impossible. How do you build a structure that can support a 100-ton locomotive traveling at speed across empty air? The Union Pacific's engineers had no cranes, no modern construction equipment, and limited materials available in the middle of the Wyoming wilderness. What made the Dale Creek Bridge special was its design. A simple yet revolutionary wrought iron lattice structure that distributed the locomotive's weight across multiple support points. This wasn't just clever engineering, it was elegant engineering that outlasted locomotives built a century later. Historical records from Union Pacific archives show that the bridge supported locomotives consistently for over 40 years without major structural failure, despite some designs predicting it would only last 5 to 10 years. For modern structural engineers, studying Dale Creek reveals why simpler designs often outperform complex ones. The principle these engineers discovered: distributed load paths over redundant supports became fundamental to bridge design worldwide. Yet this was just one of the engineering innovations that made the Transcontinental possible. Grade separation. How engineers solved the mountain climbing problem. Transcontinental Railroad faced an engineering challenge that seemed insurmountable, moving a 200-ton train loaded with cargo up slopes that exceeded 2% grade. Locomotives of the 1860s, powered by steam pressure alone, couldn't generate enough pulling force for steeper grades. Engineers solved this through a technique called grade separation. Instead of climbing directly up mountains, they built tracks that spiraled gradually, spreading the elevation gain over longer distances. The most famous example was the Evans Pass crossing in Wyoming, at 8,247 feet, the highest point on the entire route. Rather than blasting straight up the mountain, engineers designed a route that descended into valleys, climbed gradually, and used switchbacks to manage the elevation. What made this special was that it worked. A single steam locomotive could move hundreds of tons of cargo up that grade at walking speed. No helper engines required, just physics and geometry. Modern train operators still use these same grade separation principles when designing freight routes. Understanding grade separation shows why 1860s engineers had a sophisticated understanding of physics that modern railroad companies still respect. This innovation would prove essential as the railroad began moving actual cargo. The standardized rail gauge, why 4 feet 8 inches, changed everything before the Transcontinental Railroad. American railroads used different track widths, some 4 feet 6 inches, some 5 feet, some 4 feet 8 inches. A train built for one railroad couldn't run on another's tracks. The Transcontinental Railroad standardized all American railroads to 4 feet. 8 inches, the same gauge used in Britain, creating a unified network. This decision seems simple now, but it was revolutionary. The Pacific Railroad Acts of 1862 and 1863 mandated this standard gauge, and it remained unchanged for over 150 years. Modern freight yards operate on this same gauge today. What made this decision special was its permanence, and vision engineers realized that standardization meant trains could move seamlessly across the entire country, dramatically reducing shipping costs and time. Historical data shows that standardization reduced the cost of shipping grain from California to the East Coast by nearly 60%. For logistics experts today, the Transcontinental Railroad standardization is still taught as the gold standard of infrastructure decision. One final innovation completed the puzzle: iron and dynamite, the brute force. Engineering of track laying. 20,000 men put in nearly 240,000 man-hours to construct the first transcontinental railroad. Most were Irish laborers working for the Union Pacific, Chinese laborers working for the Central Pacific, and Civil War veterans who understood military logistics. These men didn't have machinery to lay track at scale. Instead, teams of 4 men, 2 holding the rail. 2 hammering spikes could lay 1 mile of track per day. If conditions were perfect, what made this special was the organizational system that made mass production of railroad construction possible. Superintendent James Casement and his brother Dan organized work gangs into teams of 100 men, each responsible for specific sections. One team would grade the roadbed, the next would lay ties, the third would place rails, and the fourth would drive spikes. This assembly-line approach to construction work predated modern manufacturing and became the template for industrial organization. Modern construction companies still use variations of this gang system when building highway infrastructure. Historical records from both Union Pacific and Central Pacific show that this system allowed teams to lay between 1 and 2 miles of track per day. Pace modern crews struggle to match even with machinery. But this brute force approach had a cost. The final innovation that made the transcontinental viable was financial genius. Government, land grants. How America financed the impossible. The federal government didn't simply hand railroads money. Instead, it granted them land, massive amounts of it. The Union Pacific and Central Pacific each received 20 million acres of public land, which they could sell to settlers or use as collateral for loans. This meant the railroads had financial motivation to finish quickly. More completed track meant more sellable land and access to government bonds, paying 6% interest. What made this financial innovation special was that it created a direct connection between engineering speed and financial reward. If you finished your section of track faster, you opened more land for sale and locked in more government bonds. This incentive structure drove both railroads to push workers harder and solve engineering problems faster than they might have otherwise. Modern infrastructure financing, including public-private partnerships for highways and bridges, uses similar incentive structures today. These 5 engineering achievements: sophisticated route finding, bridge design, grade separation, standardization, and organized labor systems, represent far more than Victorian cleverness. They represent the moment America decided to think big. What's remarkable is how few people realize that these engineering principles, developed in 1869, still guide how we build railroads today. The next time you see a freight train passing by, remember this: the track it runs on, the route it follows, and the standardized gauge beneath its wheels all exist because of Victorian engineers who solved impossible problems with mathematics, physics, and sheer determination. If you've enjoyed this deep dive into American engineering achievement, please like this video and subscribe for more stories from the rails.